one of the key problems in our really first programming project, our second lab, after writing about the differences between a mechatronic and non-mechatronic system, one of the main problems you have is doing two things at once. I've purposely written the lab so you have to learn how to do two things at once. The reason I did that is because I want you to learn about something called interrupts. Has anyone dealt with interrupts before, heard of them, know what they are? A little bit? Okay. There's two basic kinds of interrupts. There are interrupts that are triggered by an event happening. Well, all interrupts are triggered by an event happening, but an external event, an input usually was what we're thinking of. Some pin on the Arduino goes high, goes low, changes state, whatever. What an interrupt does is exactly how it sounds. The code's running along, doing what it's supposed to do. Something triggers an interrupt, and the code will pause where it's at, go jump to another section of code, deal with that, and then come back to where it left off. Does that make sense? And the reason the interrupts are useful is because they allow you to capture things that are time sensitive. Okay, they allow you to capture it and know when that event occurred if you want to know. Okay, or time sensitive things like, for example, displaying a frame on the computer, an image, right? That's part of a video stream that has to be done regularly, or else the video will tear, or it'll look odd, or it'll stop for a second and then continue. So sound also is another place where interrupts are very important. Dealing with user input, interrupts may or may not be important there. But essentially an interrupt is something that stops the code where it's at and goes and does something else. Now, like I said, there's two types. And if you go to the Arduino reference, let's see. I guess I could just link to it from Blackboard since I've got Blackboard open. Let's do that. Need to get into the 482 course anyway. Okay. Let's go to the Arduino Coding. There we go. All right, Arduino command reference. My computer does not like browsing the web and recording video at the same time. There we go. If you just go in here and you look for interrupt, there are several functions that have to do with interrupts. Look over here. You got, can you guys see that? Yeah, you can see it. Okay. You got attach interrupt, detach interrupt, interrupts, and no interrupts. What are all these things? Well, basically these are ways that you can control interrupts. Now there's a concept we need to get here. We are programming a microcontroller in a foreign language to that microcontroller. That's really what we're doing when we're inside of the Arduino Ide, which you guys have seen. Let me go ahead and bring it up. Give my computer something else to do, as if it's not busy enough. So you guys have all been inside of the Arduino Ide, I don't remember what IDE stands for, but something development environment. In any case, that's where we do our programming. Well, the microcontroller does not speak the language we're speaking. It doesn't speak C. That's why the code has to be compiled, right? It has to be converted from C to something that the microcontroller can actually understand. The microcontroller understands machine code, and machine code are just strings of zeros and ones set out in certain ways. The zeros and ones represent what the processor is supposed to do and the data it's supposed to do it on. So the Arduino Ide is an abstraction. It's something that you and I can understand more easily and program more easily and quickly at the cost of probably some optimization in the code, some space, because you can actually program in assembly language, which is very closely related to machine language. You can actually program it and program these microcontrollers. So this Arduino we've got here, the microcontroller itself was not made by Arduino. It was made by, well, it was, I think it was Atmel. Now it's Microchip. Anyway, whoever made it, that doesn't matter. It's a certain design that everyone's agreed that that's what it'll be. It's a 328P, I think, is the chip number. You can find a data sheet on this chip that'll tell you about every single thing that this chip can do. Now that data sheet's a PDF that's several hundred pages long, and it's worth referencing sometimes. But most of the time, you really don't want to get into that level of detail unless you're going to use this on an industrial scale where you're trying to get every last bit out of it that you can. I guess that was a pun and I didn't intend it because a bit is a binary digit. But you're trying to squeeze every last bit of use out of it that you can. So sometimes, though, when we're programming, we have to get into the gory details of that microcontroller to do more with it. Now, I don't really recommend going into the details if you can avoid it. If you can get done what you need to get done in a way that the code is readable, easy to program, you get it done and finished for industrial purposes, that's what you want. Okay, because you're trying to be efficient, not efficient on the hardware side necessarily, efficient in the development side. Okay, as long as the microcontroller does for the customer what it's supposed to do, who cares how efficient the code is, really? Okay, that's the idea. Now, I like efficient code. In fact, I'm a fan of efficient code. I enjoy watching demonstrations made by hackers and pirates, which are people that like to squeeze everything they can out of old machines. So if you come to my office, you'll hear me listening to some strange music that's 8-bit music and is usually written by people in Netherlands and Europe and elsewhere that are still enjoying programming the Commodore 64 in assembly language. Commodore 64 is ancient, but some of the things they're doing with it nowadays is amazing because they're just squeezing everything out of it that they can. So I'm a fan of that type of code, but there's a time and a place for everything, and most of the time when you're trying to program these in a job, or if you're trying to use mechatronics in the real world, you want to minimize your development time and make your code easy to read. So anyway, as we continue along, we will have to learn more and more about, not the Arduino, because really the Arduino is that board with the chip, but the chip itself. We'll have to learn what it is, because it has a lot of little, I guess you could call them switches, levers, controls that do many different things. And not all of that functionality is available to us through the Arduino IDE. Well, not directly. It's not available through some nice set of commands here that Arduino has, these reference commands. Okay, these are very high-level commands that are useful and great, but they don't let us put our hands on every knob and switch inside the microcontroller. Does that make sense? Okay. So as we go, things are going to start to look more and more. What I wanted to do is show you how to use timer-based interrupts. Now, I don't understand all of the details here. There are many different ways to use timer-based interrupts because I'm not really interested in all the details of this particular microcontroller. It's possible that tomorrow another microcontroller will come out and nobody will use the Atmel 328 anymore, or Atmega 328. It'll be something else. Why learn all those details? Just learn as much as you need to get done what you need to get done. So here's a nice site that I found. I looked through several before I suggested this one, and I'm going to post a link to it in the Arduino coding area. And if you read what the author has to say, he explains a lot about what this will work on, what it won't work on, and how it works. I'll explain the parts that you really need. Essentially, the Arduino has 3 timers. Timers number 0, 1, and 2. At least the Atmega 328P has 3 timers. Timer 0 and timer 2 are 8-bit timers. In other words, the maximum they can count up to is 256. A timer is just a counter that counts time events, okay, when a timer rolls over. So, or clock cycles. So, anyway, the author of this article goes through and points out that the 328 is running at 16 megahertz. So there's a clock that is triggering 16 million times every second. Okay, that's how fast it's running. And the Atmel 328 can perform an instruction on each of those clock cycles. Now, some instructions typically will take more than 1 clock cycle, but a no-op instruction, for example, which is a no operation assembly instruction, which just says to the processor, do nothing, it'll do nothing for 1 clock cycle. So that's the smallest instruction size. Anyway, so he goes on to say, well, if you think about it, if you divide out the 16 thousandths of a second, if you take 256 of those, then that's about 16 microseconds. Okay, so in other words, if one of those 8-bit counters, timer 0 or timer 2, counts from 0 to 255, it'll count every clock cycle, right? So if it counts 256 times, 0 to 255, then the period between each of its overflows, right? Because once it gets to 255, what is it going to do? It's got to go back to 0. So it'll set an overflow bit when that happens, and you can detect that as an event and make something else happen, okay? So anyway, the period would be about 16 microseconds. On the other hand, timer number 1 can count 16 bits worth, which is 65535, 0 to 65535, which is 65536 counts. Do you guys remember binary and how you count in binary? Okay, does anybody need a quick refresher on that? Are we doing okay? Looks like most of you remember. If you have questions on it, please ask and I will explain it. But so with 16 bits, you can count from 0 to 65535. When you try to count one more than that, the counter rolls back to 0 because you're out of digits, right? You've got 16 bits. All you can do is flip them all on and off. All the patterns available are 65536 different patterns. One of those patterns being all zeros. So anyway, so even the 16-bit counter, 65536 over 16 million, okay, is only about 4 milliseconds, excuse me, which is still a pretty fast period, right? That's a pretty quick. Now, do we want something to happen every 4 milliseconds? What if we want a timer, or we want some interrupt event to be triggered every second? Well, we don't have big enough timers to do that. How can we do that? Well, there's something called a prescaler. And a prescaler, I found a nice diagram that showed it, but I don't remember what it was. I think it was actually in a data sheet somewhere. But the prescaler basically takes this 16 megahertz clock and divides it out for you already. So in other words, it'll trigger, the prescaler will trigger a pulse every, say, 8th cycle, or every 256th cycle. Every time 256 clock pulses have gone by, it'll make the timer go up by 1. Does that make sense? So it looks like the clock is running a lot slower than it really is, and that allows your timer to run for a longer time in the real world. It's still counting the same amount. It could still, timer 0 and timer 2 can only count up to 255, and timer 1 can only count to 65535. But the since the timer doesn't see actual clock pulses at 16 megahertz, it sees divided up clock pulses at a much lower frequency, then the timer can run for longer. Does that make any sense? Okay. So the author of this page gave us some nice equations so that we can see how this would work. So the timer speed in hertz is the Arduino clock speed divided by the prescaler. And he noted that the prescaler can be, somewhere he wrote that it can be a 1, 8, 256, or here it is, 1, 8, 64, 256, and 1024. Okay? Now, those are the only prescalers we have available. We can't just take the clock speed and divide it by 100. That's not possible. Why? Because this chip doesn't have a switch to do that inside of it. Okay? These are the only things it has. Could we make a clock last for exactly 1 second? We can. It turns out that there's also a compare match. In other words, instead of letting the timer count from 0 to 255 and then give us a pulse, we can tell it to count from 0 to 250 and give us a pulse, or 0 to 100 and give us a pulse. You see what I'm saying? It's saying, we're done, we've reached the time that you asked for. And what this allows us to do then, this allows us the resolution that we want, so we can count to any particular amount of time that we want. Now, within reason, right? We're still limited. We still have a 16 megahertz clock, and the biggest divider we have is 1024. So why don't you grab your calculators and let's figure out what is the longest length of time any of these timers can actually time for. If you grab a calculator, I'll tell you how to do this. It's pretty straightforward. If we have a 16 megahertz clock, then that's 16 million, right? So let's start off. We can pre-scale and count 1,024 of 16 million. So it's like a tape measure where you take, 3/16 or something. So take 1024 and divide it by 16 million. That will give us a period in seconds. Because remember, the 16 million is cycles per second. So if we're dividing by 16 million, then our units will be seconds per cycle, right? So we're going to have 1024 cycles at 16 million cycles per second. So the cycles will cancel, we'll be left with seconds. Should be a lot less than a second. How much is it? So 1024 divided by 16 million. 64 microseconds? Okay, all right. So 64 microseconds, okay? And so that's 10 to the negative 6th Is that what you got?
For 64, yeah.
Okay. All right. Well, if we can count in a period of 64 microseconds, we can do that 65536 times, because 0 is included, right? 0 to 1 is a transition. If we can do that 65536 times, then multiply the number you have by 65536. That's how many times we can count that quantity of time. It's like how long our tape measure is, how many sixteenths you have on that tape measure. Okay? So now what number have we got?
That's 4.19 seconds.
So that's the most time that we can have. That's the longest time we can have between timer-based interrupts. 4 point whatever it was seconds. Okay? That's the best we could do. We don't have a longer tape measure than that. Does that make sense? Now, I don't know what kind of interrupt you'd want to run at 4 seconds apart. Maybe a temperature-based loop you could. If you wanted to measure temperature in some application, temperature usually doesn't change very quickly. Usually it takes a while for heat to infiltrate and make a body of decent mass heat up or cool down. So maybe that's an application where you would want an interrupt based on, about a 4-second period. Anyway, what about the minimum? You should be able to answer this. What's the minimum amount of time we could have, theoretically? Be 1 clock cycle, right? So 1 over 16 million. A 16 millionth of a second would be the maximum frequency of interrupts. Well, would we ever want to interrupt the processor on every single clock cycle? No, because you have no clock cycles to do anything, right? So it doesn't make sense. So anyway, the author of this page, which I'll post, this is the best one I found, says that the interrupt frequency, so say you know what frequency you want to interrupt at, is the Arduino clock speed divided by whatever prescaler you choose, multiplied by the compare match register. Now the compare match register, that's where I was telling you can tell it you're only counting up to 100 or 101 or whatever, okay? You're not going to count the full 255 or 65535, okay? Now, you can rearrange this to solve for the value you need to put in the compare match register in order to get a desired input or interrupt frequency. Now, why don't we go into Excel and make our lives easy? What on earth? There we go. That's what I expected before. Asked my poor little computer to run one more thing. Now, in our particular problem, we want some music to play while some lights flash. Now, what I want to do, I'm not going to program a solution to Lab 2 for you guys. I'm going to give you pieces along the way and have you put it together. I'll also create a solution and show it to you once you show me yours. But this is a piece of the puzzle along the way. What would be reasonable, do you think, for turning on and off LEDs? What I want to do is I want to take these 8 LEDs and I want to choose one at random and turn it on for a random amount of time. Say maybe 1/10 of a second, right? So maybe I'll choose an LED, turn it on for 1/10 of a second. Maybe I'll choose another one, turn it on for 10/10 of a second. So my resolution is 1/10 of a second. Does that make sense? Because if I turn the LED on and off any quicker than that, your eye might not be able to see it come on. Okay, so I could have an LED on for 1/10, 2/10, 3/10, 4/10, 5, 6, 7, 8, 9, 10/10 of a second. I'll never leave an LED on for longer than 1 second. But I want to choose an LED at random and choose a random amount of time for that LED to be on, units being 1/10 of a second. So how often do I need to interrupt the program that's playing the song? Because we've got a nice song playing program. You guys have already discovered that. I'll bring that up in just a minute for the Anderson students. Okay, but how often would I need to interrupt? Well, I need to interrupt the code every 1/10 of a second. Does that make sense? So my frequency, my interrupt frequency that I desire is 10 hertz. So let's type in some things and do some calculations to figure out. Here, let me slide this over here. There we go. And let's put this over here so we can see it. Computer's running slow. I wonder how smooth that transition will be on the video. Probably not very. Okay, so Let's see. That's where it's not solved for. Let's go here. Here we go. So desired interrupt frequency, I said, is 10 hertz. In other words, I want the code to be interrupted 10 times a second. Is that a lot of interruptions? In a second? Right. From a human being standpoint, it seems like a lot, but from a processor that's doing something 16 million times a second, that's not very often. Okay. In fact, we could figure out how many clock cycles the processor would have in between each of these, right? If we just interrupt for one clock cycle and come back, how much time would there be between them? Well, you just take the 16 million divided by 10, right? Okay, so that's 1.6 million. So it has 1.6 million clock cycles between interrupt. Now it's going to be less than that, of course, because once we go into the interrupt, that's going to be code that's running also, and that code is going to take some time from the processor. Guys, if what I'm saying goes over your head, please stop me. Okay, I want to make sure that I'm clear and you understand this. If I'm going too slow also, please let me know. So desired interrupt frequency is 10 hertz. Okay, what about the prescaler? Well, the prescaler, we learned, can be only one of a couple different values. What were they? 1 was one of them. I think 8 was another, if I remember right, 64, 256, and 1024, but we'll verify that in just a moment. Those are, I believe, our options. Let's go back up. And now, where would we get this data? If we didn't have somebody that had written a website that explains this to us, how would we know? Well, we could go dig through that PDF document that's huge that talks about everything that this little microcontroller can do. That can be difficult, but it can also be fruitful. It can be useful. Obviously, this guy's already done it for us, so we won't bother. So let's see, 1, 8, 64, 256, and 1024 are the numbers we can use. Okay, great. So now I don't know what prescaler I need, so I'm just going to guess 8 to begin. All right. So the compare match register, what we need to put into it is equal to 16 million divided by the prescaler, which is multiplied by the desired frequency, minus 1. So let's set up an equation to do that. So compare match register will be equal to 16 million divided by, and I'll put it in the way that he has it, but then I'm going to change it. Divided by the prescaler, which is multiplied by the interrupt frequency in quantity minus 1. And minus 1, if you read what he says, has to do with the fact that we're counting from 0. Okay, so that's fine. There we go. So the compare match register would need to be 199,999. The problem is that the compare match register is itself a 16-bit register, which can only hold up to a maximum of 65535. Now, it's a little more complicated than that. He makes a note here. Remember that when you use timers 0 and 2, this number must be less than 256 and less than 65536 for timer 1. Why is that? Well, because that's the maximum that those timers can go up to. We're telling it, count to this number, and that'll give us the interrupt frequency that we want. Well, it can't count. None of the timers can count up 199,999 cycles worth of time. It just can't. They don't go that high, right? So which are we going to use? Well, let's say we want to go for either timer 0 or timer 2, because that timer, well, actually, let's use the good one. Let's use timer 1, because it has, it's the biggest timer. So let's try for it. 65536, we'll go for that one. Now, this is still too big, so what can I do? Well, I can divide down the clock frequency a little finer, right? So let's set the prescaler at 64. That'll cut down on how high the timer 1 needs to count. And now we're down to 24,999. Well, timer 1 can actually count that high, because that is less than 65535. Could we do any better? Well, let's see. If we take it to 256, then that timer only has to count up to 6,249. What if we go to a 1024 prescaler? So we're really dividing down the clock cycles to about 1,024. Well, then we have to count a half of one of those cycles, and that doesn't work. So I'll go back up to 256 to get the exact resolution we want and have exactly 10 interrupts per second. Does that make sense? Can you guys see this okay? I've forgotten. I should have zoomed in for you. So all I'm doing is using this equation to figure out how far to make the timer count in order to have the timer give us a pulse every tenth of a second. So 10 pulses per second. So if I set the prescaler to 256 and the compare match register to 6249, I should get 10 interrupts per second. Okay? Now, all this seems theoretical so far. Why bother with all of this? Well, down here, he gives us some nice code that shows us how to do it. Now, you'll notice here he's got his setup. CLI stands for clear interrupts, which means turns off interrupts, because you can actually make interrupts not happen ever if you want. And that's what CLI does. He does a bunch of stuff that seems really confusing. Here, let me zoom in so you can see this. Oh, it doesn't really zoom in well on this. Tell you what, let me just copy this code and I'll paste it inside of the Arduino Ide and we can look at it. Nope, that's too much. Let's try one more time. I just want to there. Copy, Control A, Control V. Okay. Now let's look at this code and see what it does. It can be difficult to understand. We've got CLI for stopping interrupts. It's nice that he commented the code. We can figure out what it does. I want to point out something. There are many times when there are lower level commands that the Arduino will actually understand that you may not. Yeah?
Can you change the zoom of that window so we can see the left side?
Yes, thank you for reminding me. I always forget. Is that better?
Yeah.
Okay, thanks for reminding me. Yeah, for the Anderson students, if I make this full screen, the left-hand side drops off of the TV we've got up there for the students to see, so they can't see what's going on. So CLI is supposed to stop interrupts, and then they've got this TCCR0A equals 0. What the heck is that? Well, a lot of times when you see something like this, it's not a variable that has been declared. This is a register or something that is a unique name to that chip. Does that make sense? It's something it's a register that chip has that you can work with. And if you specify that TCCR0A in your code, you're talking about a very particular register. You can't use that as a variable name. It won't work because it's already used. It's already a name somewhere. Okay? So to understand what all these things do in detail, you would actually have to go into the data sheet for that chip and look it up and find all the registers and see what they're all for. Like I said, this is one of those things where there's a bunch of different knobs and switches built into it that you have to know. You have to know what they do so that you can toggle them if you wish. And the Arduino language does not give you direct access to these, except if you know what they're called, you can do something with them. It doesn't have nice commands with nice names to help you work with these things. Now, I don't really care what all these things are. As far as I'm concerned, I can look at this and understand, set timer 0 interrupt at 2 kilohertz, okay, so 2,000 interrupts per second. Timer 1 interrupt at 1 hertz, so 1 interrupt per second. And timer 2, he's changing all 3 timers so that he can set their interrupt frequency. These are all going to be timer-based interrupts. They're all going to interrupt the processor at these various frequencies. So timer 2 is asking for a lot of processor time. Every, 8,000 times per second it interrupts the processor and it says, hey, come here, do this for me. Okay, that's a lot. Let's get rid of timer 2. I don't really have an interest in changing all the timers. In fact, I really only need to change 1. But I'm going to try and break the code on purpose and show you how you can get into trouble using this stuff, and hopefully show you how to get out of trouble too. What I'm going to do is simply let it work on timer 0 and timer 1. And what I'm going to do is I'm going to leave timer 0 alone. We said we'd try to use timer 1. I'm going to try and change these settings so that it will interrupt instead of at 1 hertz. I want it to interrupt at 10 hertz, 10 times per second. Now, if you start looking up these registers, you'll find out that we really don't need to do anything here. This is just clearing a couple things. Initialize counter value to 0, that makes sense. We don't need to change anything. Set compare match register. We want 10 hertz increments, and we calculated what the compare match register should be. It should be 6249. So instead of 15624, we need 6,249. That's the amount, that's the number of time counts we want timer 1 to go up to before it interrupts. Notice it's a lower number than what we have here, okay? And notice that they're using the very equation we used in order to calculate the compare match register. There's only one difference. We're using a different prescaler. We're using 256. They used 1024. So let's change the comment, not that it matters, but for our own memory's sake and for people coming after us to understand this, let's change the comment to show the equation we've actually used and our result, 6249. So here's where we'll set the compare match register. So I guess the name of the compare match register for timer 1 is OCR1A. I don't know why they called it that. I don't care. That's just what I need to change. Turn on CTC mode. If you read in that article, you see that CTC mode is where the timer doesn't just overflow and set a flag to indicate that it's done. It compares instead. It goes to the number we've set to compare. So it makes sense to set the level that it's supposed to go up to and tell it to go to that level. You see what I'm saying? Unless we tell it to go to that level, it's just going to count all the way to 65535 and completely ignore what we've put in here. Now, I started looking into exactly what this does, and I understand it, but why bother? We don't really care about this. What we care about is right down here. So you turn it on CTC mode, great, that does it, that's fine. Set CS10 and CS12. Well, I kind of flew through this part. I'm not going to go through it in detail, but basically there are 3 bits that you set. Now think about it, 3 bits. How many combinations are there of 3 bits? Well, you got 0, right? You got 1, excuse me, you have 2, you have 3, you have 4, looks like gang signs here in a minute, you have 5, you have 6, right? Did I forget one? 7, there should be 8. Somewhere I missed one. Did I miss counting
all
one?
zeros.
I forgot counting all zeros, I think. Okay. So there are 8 different combinations with 3 bits. Well, how many different prescalers are there? Well, we got 1, 2, 3, 4, 5. You can't represent 5 different things with 2 bits. You can only represent 4 different things, right? 0, 1, 2, and 3. 0, 1, 2, and 3. That's all you can represent, right? So we had to have another bit to have another prescaler. So basically CS 0 through 2 are used for selecting the prescaler. Does that make sense? Where I think it's 000 is 1 hertz. 001 is, not 1 hertz, 1 for the prescaler is 8, and then 64, 256, and I think 100 is 1024 for the prescaler. I feel like I'm not explaining this well. Do you guys understand what I'm saying? It's just flipping switches to choose the prescaler is all it really is. Okay? So if you look at this, you'll say, well, CS10, CS12 bits for 1024 prescaler. I was wrong. I told you the wrong combo. Somewhere in here he talks about the combinations that you use for setting the prescaler. And you can look at this and you can say, well, why is it this way? Why would this make sense? Well, this is not something you can say from a computer science or any other standpoint, this is the way it should be. This is just the way that the people that designed this processor made it. It's like the people that designed this operating system put a start button right down there. Okay, it doesn't have to be that way. If you use a Macintosh, it's different, right? So we have to learn exactly how they designed it and how, what all we can do with it. Now, up here there was a nice graph. Here we go. That'll tell us. All right. So you got CS00, CS01, CS02. That first number, that 0 there, indicates that you're talking about timer 0. If you wanted to talk about timer 1, it'd be CS12, CS11, and CS10. Okay. So you've actually got 3 sets of 3 switches to deal with timer 0, timer 1, and timer 2's prescaler. Okay. Now, if we set it at 000, no clock source, timer counter stop. So there are other options besides the 1, 8, 64, 256, and 1024, and that's why we need 8 bits. It's not just because there are 5, it's because there are actually 3 others. There are full 8 options. if we want the prescaler to be 8, well then we need to turn off bit 2, turn on bit 1, and turn off bit 0. Now, which prescaler did I say I wanted? 256. So if I want a 256 prescaler, then I need to turn on bit 2, turn off bit 1, and turn off bit 0, right? Now, by default, the bits are off, so really all I need to do is turn on bit 2. Since I'm dealing with timer 1, I want CS12 set. So I want CS12 to be on. Now, notice how he's saying he's setting, or turning on, CS10 and CS12. So he gets a 1024 prescaler. Well, sure enough, if he sets CS12 and CS10, he will get a 1024 prescaler. That's not what I want. Instead, what I want to do is only turn on CS12. Okay? So I'm going to get rid of this in the comment. Well, before I do, let me change the code. Now, it's pretty easy to see that this is dealing with CS12, and this part is dealing with CS10. This is an OR command between the two, and basically what it does is it just takes these two bits, puts them in the right position, and turns them on in this register. This is the register where we get to set those 3 bits. Okay? Now, I don't care about that so much because I can just see that I need to get rid of CS10, and I don't need the OR because I'm only doing one thing. So now I'm not dealing with CS10, I'm only setting CS12 bit, and it's for a 256 prescaler. Do you guys understand what I just did? Kind of? Sort of? All right. And then enable timer compare interrupt. Okay, fine. So it's interrupt. So it's set. It's capable of interrupting. Now SEI then means set interrupts. It turns the interrupts back on. Now, this was a lot of guesswork, right? I didn't go deeply into the data sheet to figure all this out. And I didn't have to. What I want to do is show you that there is a relationship between the Arduino language and some of the stuff that's innately available to these microprocessors or microcontrollers. See that SEI and CLI? Clear interrupts and set interrupts, and basically turn interrupts on and turn interrupts off. If you look, there are interrupts and no interrupts commands. And if you read the description, interrupts, if you issue that as a command, it re-enables interrupts. Well, that sounds a lot like set interrupts. In fact, they're exactly the same thing. CLI, well, no interrupts, the command, is another way of writing CLI. In fact, if you look in the Arduino header files where they define some of these things, they simply define no interrupts as CLI. So the compiler, wherever it sees no interrupts, it literally replaces it with CLI, to clear interrupts. There's no difference between the two. So it's just another word. Now, is CLI or no interrupts easier to understand? Obviously, no interrupts is easier to read and to understand. That's why they created it, right? But basically, all these functions that Arduino gives us are just nicely named things, and sometimes they do a little bit more than just changing the name. In fact, most of the time they do a lot more than changing the name, because the Arduino environment works not only with the 328 chip, but with other chips as well. So one of the advantages of going to a C-like language and abstracting it more is that you have code that is compatible, if the compiler understands it, with multiple different microchips or microcontrollers. So we can write code in Arduino and download it to an Uno that's using a 328, or download it to a different Arduino that's using a different processor, and both work. Because we're not hitting registers directly. See, it's possible, in fact probable, that the other microcontrollers we could get on a different type of Arduino would not have these exact registers. That's one of the problems we'll run into. This code is only going to be good for the 328 chip because we're talking about 328 registers. It could be that a different chip only has 2 timers or 1 timer, okay, or maybe it has more. And so the hardware details change from chip to chip, or microcontroller to microcontroller. If you can write in C and have a compiler that compiles it for the chip you're interested in, then you can write code for many different processors. An analogy to this, some of you probably have Android-based phones, and others of you have iOS-based phones, right? Well, if you're writing a program, I like to play Genies and Gems. It's an old game. It's an old match game. So every now and then I'll play it on my smartphone, okay? I enjoyed it. I'm up to like level 500 and something. I don't remember where I'm at. So I just play it every now and then for a few minutes and just, keep slowly moving along. Well, if you want to distribute this game, you want to make money off of it, right? That's the purpose of writing the game. You really don't want to rewrite that game in another processor's language. You want it to work on both Android and iOS. So when you write a game like that, you write it as high level as possible. So the algorithm of, if these 3 gems in a row match, then they need to be cleared. That algorithm is the same no matter what you put it on. The way the code should work, the way the code should think, is the same regardless of the processor. But the details about exactly what levers to pull to turn a pixel on to light up that or to turn it off so that that gem disappears, that's a detail specific to each processor. Okay, and so you have to have a compiler that takes the code, right, the C code that you write, the algorithm, and translates it into different processors. And that's essentially what we're doing here. So one of the problems with this low-level language we're working in is it won't work for all the different processors that are available. Now I think I've also got I might have one more problem in my notes. Yeah, I need to make this a 10. Because remember, that was the desired frequency was 10 hertz, not 1 hertz, which we changed from. Now I'm purposely leaving in timer 0. I'm hoping it will mess up my code, and I'll show you why. One thing that's important when you're just copying and pasting like this is to get rid of everything you don't need. Because you don't want things messed up that are already working. And I'm leaving this in so that hopefully timer 0 will be messed up and you'll wonder what's happening. Okay, so now let's go down to the rest of the code, because remember, this is just the setup portion, right? Void setup. So we're at the point, well, we're not done with setups. Well, he says we are. Let's see, I think that I know what happened. I copied a lot of text that I didn't need. Yeah, I ended up copying some text from the article, so let me get rid of some of this. This is just text from the article. Let's see. And then the next, I accidentally copied 2 sections of code. Notice that this is just the setup portion, where the timers are set so that they will interrupt the processor at our desired frequency. Make sure I'm still recording. Yes, good. My computer all of a sudden is responding smoothly, and so I thought it might have stopped recording video. Okay, now let's see. This is basically the same thing. I'm going to get rid of the header part. I'll show you what I did. I accidentally copied code from this section and code from this section. This section has a little bit more, and I'll explain what it is. Let me get rid of the excess part, and I'll explain the part we've now added. Let's see. Yeah, let's just get rid of this part so far. Okay, this was the setup that he had before. He's just added a few things where he's defined some pin modes. And so what he was going to do is just basically make some LEDs flash at different rates. That's all he was going to do. I want to make 2 LEDs flash at different rates. So instead of having 3 timers, I'm only going to have 2. So we don't need anything that deals with timer 2. So let's get rid of this toggle 2 variable, and let's get rid of one of the output pins. And of course, I've already written the setup part from CLI to SEI the way I want it, so that the timers will behave as I wish instead of what he had. So let me get rid of that part of the setup and copy or move the variable declarations and the pin declarations out. Now we've already got a void set up, so let's get rid of that. And I'll need to get rid of one here. Okay, but let's move these up into the void setup we already have. So we'll cut that out. These are just variable declarations and pin modes. That's all that we've really added so far. All right. Now, what's been added are what are called interrupt subroutines. Now you can say, okay, I get that we've got timers running and it's going to interrupt the processor, but what's going to happen when the processor, why are we saying we're interrupting the processor? What is the processor going to do when we interrupt it? Well, essentially all that happens is, let's say for timer 1, the one we're interested in, every 1/10 of a second, what's going to happen is the processor will be interrupted and an interrupt service routine called. That's what ISR stands for. So in other words, every time that timer 1 reaches the predefined compare value, that's 6,249 or whatever it was, this subroutine from here to here is going to be called. And we can put whatever we want in that subroutine. What he has right now is pretty straightforward and easy to understand. Now it's actually 10 hertz, we changed that, right? So 10 hertz, we got to double all this. And he's got a bug in there, it's not kilohertz, it's hertz. Okay. So generate pulse wave of frequency 10 hertz over 2, 5 hertz, it takes 2 full cycles to toggle high-low. What is he talking about? Well, he's got a variable. That variable is toggle 1. Remember he defined it above. Okay. He's going to do a digital write out to a pin to turn on that pin if toggle is already on, and then turn toggle off. When and then that's the end of the subroutine. When the timer causes the processor to be interrupted again, we'll come into this code again, toggle will be 0, so we'll go into this section, write a low out, and turn toggle back on. Do you see this? All he's doing is turning an output pin on and off each time he comes into this subroutine. And that way he can make a light flash on and off. And that's what he's talking about up here. Since we're going to interrupt the processor at a frequency of 10 hertz, then basically the light's going to flash at 5 hertz because it's going to be on for one interrupt and off for the next one. On and off. It'll do that 5 times every second. That's 10 total things, right? 5 ons, 5 offs in 1 second. Now, I've got to fix something because I blew away his definition of using pin 13, and I also got rid of using timer 2. So let's see where this ends. Where's the matching? There it is. Yeah, so let's get rid of the interrupt service routine for timer 2 because I said I didn't want to bother using it. Okay, I'm going to work with timer 0 and timer 1. And here's the beauty of all this. These 2 interrupt service routines that are being triggered by 2 different timers can be called even though we're down here in this loop playing music. Does that make sense? Now before I actually put something in here, what I'm going to do is let this run on the Arduino we've got here, and I'm going to let you see that the lights flash. Now the pins that I've got hooked up are different. I've got pins, let's see, 4 through 11 are connected to 8 LEDs. Okay, so I'm going to use pin, say 4 and 5. That's fine. So we're going to change this to pin mode on pin 4 and pin 5. We'll change those to outputs, and those are the ones we'll actually affect. So let's change the digital write to pin 4 and to pin 5. And by the way, don't worry guys, I will post all this code for you once I get it done. What I'm going to post for you is a bit of code that will play music and flash LEDs at random. Okay? And we're almost there. We've gone through the long part. So pin 4 and 5 are the ones we're using. There we go. Okay, so I think this should work. Let's make sure everything's okay. We need variables toggle 0, toggle 1, which I think we have. Yep, that's set. And we should have an LED that flashes at, well, 1,000 hertz, right? And we should have one that flashes at 5 hertz. And doing nothing else in a loop. We still have a place down here where we can do whatever we want, like playing music, which we'll do later. So let's download this to the Arduino and see what happens. Let me hook up my Arduino. And for the Anderson students, I'll make a fritzing sketch of this and put it on top of the I've already got it set up to do. I was playing with this the other day and have my code. Let me, let's see, hang on. Uh-oh, we don't have connection to it. Let me save this. I'm going to make a fritzing view of this so you can see how the circuit's laid out for those in Anderson. Let's say save as, and that's fine. Let's call this now. It will not like it if I have spaces in the names, so there we go. Okay, let me close it, start it up again, and see if it will connect to the Arduino this time. If not, I'll move the port and see if it will respond then. I was hoping to get to the point where we could run some code before we have our break. Port is still not happy with me. Try plugging it into another USB port. I don't really want to hear that right now, so I'm going to disconnect it. Still not happy. Let me go into Device Manager and see what it's doing. Yeah, it sees the Uno on COM 13. Respond to me, come on. There we go. Alright, now it's got it on COM 13, and I just made that full screen. There we go. Alright, so now let's download this code and see what happens. So compiling sketch, what does that mean? What does it mean to say that it's compiling the sketch? It means it's converting these instructions the chip can't understand to something it can. That's what it means. It says toggle 0 is not defined. Well, toggle 0 is a variable that is used inside of an interrupt subroutine. What did I tell you about variables that are used inside of an interrupt subroutine? Do you remember? They need to be declared volatile. Let's see if that helps. And basically, this just tells the compiler, and still doesn't like it. It tells it that this is something that can be changed outside of the interrupt subroutine. Let's see. Oh, I need to declare it.
Try declaring it as bool, not boolean.
It recognizes Boolean. I don't think that's the problem. I think I need to declare it outside of setup. Because otherwise it is a, yeah, it was a variable that was only declared inside of setup. Does that make sense? It needs to be declared globally instead of locally, because it was declared inside of a function. Does that make sense to everybody? Do you see why it didn't work? Okay. Okay, now, if you guys want to come over here and look at this, you'll see something interesting. What do you notice about those two LEDs? Anderson students, I'll hold this up so you can see it working also. Hopefully I don't short anything out, and I hope you can see that. Somebody else is using the Mario theme music. So what do you guys notice?
One's staying on.
Is it really staying on? There's one flashing. It's about 5 times per second, but the other one is blinking 1,000 times per second. So it's dim to us, right? We can't see it turning on and off. Did you know that if you have a remote control at home with your TV, it's actually flashing? Okay, you can't see it. You can actually use, especially if you have a cheap cell phone like I have, you can look at the LED It's an infrared LED, and you can usually see it lighting up, and you can tell if your batteries are good or not. Well, it's actually, when you press a button, you'll see it come on and off, but when it looks like it's on, it's actually pulsing. It's sending data because it's trying to send commands to the TV. So your and my eyes can't see that LED flashing, but a fine enough sensor can see it turning on and off at 1,000 times per second. Our eyes have the resolution to see that second LED turn on and off 5 times a second. So why is it 5 times instead of 10? Well, like I said before, one interrupt turns it on, the next interrupt turns it off. So we only get 5 ons in 1 second. Plus 5 offs is 10 hertz. So this is working. Life seems good. Right? Any questions about what I've done so far? Now, what else could I do? Well, I could go into this code and I could write here that the Arduino should be doing something else like playing music. Right? So that's what we're going to do. Not right now, but why don't you guys take your 5-minute break? I've been talking for an hour. And then when you come back, we'll put some music in here and see if we can make it work.